Okay, so let's reconvene. So let's start the afternoon session. Okay, please. So the first speaker of the afternoon will be Chun-Ye Chu, and he will tell us about searching for new physics in coherent neutrino scattering.
Okay, no problem. Okay, so hello everyone. So first, I would like to thank the organizers for the invitation. My talk is about searching for new physics in coherent neutrino scattering. I think probably you all have heard of coherent neutrino scattering since last year when the Coherent Collaboration announced the first observation of coherent elastic neutrino nucleus scattering. This was important news in the neutrino community. Why is this so important? One reason is, of course, they have achieved the observation successfully for the first time. But more important reason is that using this process, we can build very small neutrino detectors, unlike the conventional neutrino detectors, which are always very huge. Since the first publication of this process, it has been a hot topic. Here you can see the original publication has received 89 citations in 1 year. Among these citations, a lot of people are working on new physics. So today I'm going to talk about what kind of new physics could be relevant to this process. I'm going to talk about the so-called non-standard interactions and also more generalized Fermion interactions, including scalar, pseudoscalar, vector, axial vector, and tensor couplings. And then there have been studies on stereo neutrinos, light mediators, and neutrino magnetic moments. Finally, if neutrinos interact with dark matter could also be relevant. So first, let me briefly introduce coherent elastic neutrino nucleus scattering. Consider a neutrino scattering of a nucleus with Z boson as the mediator. If the neutrino energy is very high, then of course it will just smash the nucleon and produce very complicated final states. But if the neutrino is not so energetic, then this becomes an elastic scattering process. For elastic neutrino scattering, there are two different scenarios. If the neutrino energy is relatively high, then the neutrino wavelength will be much smaller than the nucleus radius. In this case, the neutrino will interact with each neutron and proton inside individually, which means there's no coherency. So the total cross-section is simply a sum over all these proton and neutron cross-sections. But if the neutrino energy is very low, then the neutrino wavelength can be much larger than the nucleus radius. In this case, the neutrino cannot feel the internal structure of the nucleus. So it just interacts with the whole nucleus. So instead, we do not sum over these cross-sections. We sum over these amplitudes. And when you take the square of these amplitudes, the total cross-section should be much larger than the case without coherency. And because we sum over the amplitudes and then take the square, so the total cross-section should be proportional to the square of neutron and proton numbers. This is the differential cross-section of coherent neutrino scattering in the standard model, assuming the full coherency. Here, T is the recoil energy of the nucleus, and N and Z are neutron and proton numbers. Tmax is the maximum recoil energy that can be caused by a certain neutrino energy, and it's purely determined by the kinetics. Here you can see that this part is proportional to neutron and proton numbers. And in particular, something interesting here is for proton numbers, the weak charge is proportional to 1 minus 4 sine theta W squared. And in standard model, this value is quite small, I think about or 0.203. So in a good approximation, you can say, well, the differential cross-section is roughly, this part is roughly proportional to n squared. But the mass of the nucleus is also proportional to neutron and proton numbers. So the differential cross-section is roughly proportional to n to the third. So you can imagine that if the neutron number is very large in the nucleus, then you will have a very large cross-section. However, if the nucleus is very large, indeed the cross-section is very large, but the recoil energy have to be very low. So here I can show you something like if for one MeV neutrinos, for germanium nucleus, the recoil energy is about 0.1 keV. This is actually below the current detection technology. However, you know that dark matter directed detection experiments also require very sensitive detectors to detect very low energy. So after many years of developing in this ultra-low threshold detection technology, we are finally able to detect coherent neutrino scattering. Because coherency requires relatively low neutrino energy, and also if you want to observe it, also you want intensive neutrino source, and typically there have been two neutrino sources considered. One is pion decay at rest produced by spallation neutron source, which is used in last year's coherent coagulation. And another possibility is to detect reacting neutrinos. The advantage of spallation neutron source is neutrino energy is relatively high, about 20 to 50 MeV. So the cross-section will be larger. And reacting neutrino, because the neutrino energy is low, so usually it requires much lower threshold, so it's more difficult. But when you do have very low threshold detectors, you can get super large event number. Here I show you an example. Assuming you have 100 kilogram germanium and you have achieved 0.1 keV threshold, and you just put this about 10 meters away from a 1 gigawatt nuclear reactor, then by simple estimation, you can get 7.6 million events every year. So you see, this is a huge number. There are several important implications of such a large number. One is, of course, you can build very small portable neutrino detectors. So maybe in the future, you can just build a neutrino detector so small so that it can be put into your suitcase or put on your desktop as possible. Another thing is, with such a large event number, you can achieve precise measurement of neutrino interactions and electroweak parameters. For example, there have been studies on using coherent neutrino scattering to measure the electroweak mixing angle. Before I show you that, here it is very sensitive to the deviation of the theta w, sin theta w to 1/4. So when you see some small deviation from 0, you can immediately see the effect. And they have been estimated.
The value is 233. This is your value, 233.
233.
Yeah. 18th value.
Yeah. Yeah. I mean, just, probably central value is not very important. You just say roughly 1% precision. That's what I want to say. Yeah, and of course, with such a high precision, you can. Okay. Of course, with such a high precision, you can try to find new physics. And now I'm going to talk something about new physics. I have done a search in the literature about what people have done on, for new physics in coherent neutrino scattering. And here you can see a lot of papers. If I miss your paper, just let me know. Apology for inverse. I'm sure that I have included most of papers here. And here you can see non-standard interactions and light mediators are the two most studied topics recently seems like light mediators has been popular. And also non-standard reaction is always a popular topic in neutrino physics. And in addition to that, there are also studies on more generalized Fermi neutrino interactions with all these different Dirac matrices. And then stellar neutrinos, neutrino magnetic properties, not necessarily magnetic moments, but also electromagnetic properties such as the charge radius and other stuff. And
Charge radius not Ku radius.
the charge radius, yeah, I'm not sure. Yeah, but I think most people actually focus on neutrino magnetic moments. And finally, this is a recent paper by me and my collaborator, and he insisted me to put this here, so I also put this here, although I feel that it may be a little bit offline. So first, let's come to non-standard inflections. This is the usual Lagrangian considered for non-standard inflections. Typically, when you have the physical motivation is clear. When you have something like a new gauge boson, such as Z prime, and you integrate it out, then you obtain the so-called non-standard inflections. And of course, sometimes it does not have to be a new gauge boson. If you have some scalar or other inflections at loop level, you can also produce non-standard inflections. A very important feature of non-standard inflection is that it has left-hand flavor violation. If all these epsilons with flavor off diagonal elements exist, then there's left-hand flavor violation. That was one of the motivations, original motivations proposing this. I think the earliest work was by Wolfenstein, who proposed this as one possibility to get neutrino flavor translation in matter. Another important thing you should notice that this is still in a V minus A form. Why? Because you do not introduce right-hand neutrinos. You only introduce left-hand neutrinos and new interactions for left-hand neutrinos. So the interaction must be V minus A. This is important when we are going to generalize this to other forms, which we will see in the next page. The effect of non-standard interaction in coherent neutron scattering is quite simple, or in other words, quite boring. You just replace the weak charge by a non-standard interaction charge, and the non-standard interaction charge is it depends on these small epsilons plus the standard model parameters. And of course, you can ask questions like, why this must be gamma mu and V minus A gamma mu? Sure, you can indeed extend that. For example, if you have other particles, other mediators, such as scalar mediators or charged scalar, all that stuff, then you can integrate out. And this is the most general Lorentz invariant interactions. It includes all possible combinations, scalar, pseudoscalar, vector, axial vector, and tensor. And there's something you should notice, because here we do not have V minus A form, which means sometimes you actually introduce right-handed neutrinos. And also because the right-hand neutrinos in this process can be produced in the final states. So it means sometimes right-hand neutrino signals could appear in neutrino scattering. And in principle, if you observe some new interactions, you can use this to distinguish Dirac and Majorana neutrinos. For example, if you indeed observe right-hand neutrino signals, then probably it implies neutrinos are Dirac particles. Another thing, maybe some people may feel that the tensor interactions is a little bit exotic, but it is not. There has been a very good motivation for tensor interactions, assuming you have charged scalar. And when you integrate out the charged scalar, you have to make a field transformation, just like what you have done for the W boson in the stand model. You have to make field transformation, and after field transformation, typically you have sigma mu nu, the tensor form. Okay, because there have been so many paper studying non-standard interactions, so I don't want to present the details of all their analysis and results. Here, just give you a brief summary of what is the current status and what is the future. Currently, for all these effective interactions, no matter it's non-standard interaction or more generalized form, typically you have like 10 to minus 1 precision. And also you should notice that because for non-standard interaction, you just have one measurable parameter, the effective charge. So, and you also have a lot of epsilons here, so which means there are a lot of degeneracies in parameters. What about the current status of from other constraints? You can go to these reviews. This is non-standard interaction reviews, and typically it's from 10 to minus 3 to 10 to, sometimes it's out of 1. Depends on the flavor, all that stuff. So you can see that this could be at least complementary to some bonds, non-bonds. In the future, we could achieve 10 to minus 3 or 10 to minus 2 because in the future, reactive flux will be measured, I mean, using this coherent scattering process. Okay, I will go quick. And then there have been starring neutrinos because usually this coherent neutrino scattering has very short baseline, so it is sensitive to large data m square. Here, for example, some guys shown that this well-known LSND item could be excluded in the future if you have relatively optimistic configuration. And then there are light mediators. Usually it is such process is very sensitive to all this low energy stuff, and in some parameter space it has leading constraints depending on models, of course. And neutrino magnetic moments. In the standard model, if neutrinos are massive, you can already have neutrino magnetic moments, but that's super small. Just by this group, But if you have some beyond standard model physics, in principle, neutrino magnetic moments could be enhanced a lot. But as far as I know, it's still probably difficult to produce very large neutrino magnetic moments achievable by these experiments. Something not so good is it's still not better than neutrino electron scattering, because neutrino electron scattering is more sensitive to low recoil. So you see the gamma experiment have this sensitivity, not sensitivity constraints, but all the other coherent bonds are not so strong as gamma bonds. And there have been recent charge radius studies which also gave some constraints on the charge radius of neutrinos. And finally, a work done by my collaborators and me, we consider something like the final states is not a standard model neutrino. It could be some dark particles. This is possible. For example, one situations like this, and we indeed studied the possible signal in coherent neutrino scattering because this could be massive. So it will also have cause some spectrum distortion in the coherent signal. And for some benchmark, it is possible to get the correct radical abundance of dark matter, assuming this is dark matter. So basically, you can regard this as the inverse process to search for dark matter. Typically, we just search direct scattering of dark matter. In this case, you use neutrino to hit on target and produce dark matter. So roughly, you can say it's inverse search for dark matter.
Where does dark matter come in?
Yeah, this one.
Oh.
Yeah. And finally, that's a summary. We say that elastic neutrino scattering is powerful in probing both neutrino, both standard model and beyond standard model neutrino interactions, because using this you can achieve high precision measurement of neutrino interaction. And recent coherent experiment has already shown you some good constraints on all these kinds of new physics. future reactor-based coherent neutron scattering will reveal more of unexplored space of new physics related to neutrinos. Yeah, that's all.
Hi.
Hi.
Can you go back to the slide with a cross-section, please?
Slide about cross-section, sure. This one, right?
Yeah, right. So, first of all, I don't see the cross-section to be there.
Yes.
Sorry, the form factor to be there. And,
yeah, form factors, I
yeah.
didn't write it out, but it should be something just in front.
Sorry, what?
Sorry?
Can you repeat, please?
Can you repeat your
answer? I mean, I didn't put form factors just for simplicity.
Oh, okay.
I mean, for completeness, of course, you should put the form factor, and you know that the form factor will approximately should approximately be 1 if it's for coherency.
Yeah. But it's included in your limits.
Yeah. In your data analysis, you must include that, but this is, I want to stress that the dependence on neutron and proton numbers.
Okay. And another question is, I can see that you have dCdt. It is approximately, it goes essentially with neutron number squared, in neutron number cubed, but it should be with neutron number squared, right?
The total cross-section, this is differential cross-section. Differential cross-section is proportional to n to the third. And for the total cross-section, you should integrate it over recoil energy, and because the maximum recoil energy is proportional to inverse of m, so roughly you have something like n to the second, n squared. The total cross-section is indeed proportional to n squared, but the differential cross-section is n to the third.
Okay.
Yeah.
So my comments on this neutrino electromagnetic properties.
Okay.
I have done that long time ago, 1976. As I didn't intend that somebody will talk about this neutrino magnetic moment. In 76, I showed my transparency.
Okay.
I have written paper, calculated neutrino magnetic moment, tried to obtain very large magnetic moment in relation to neutral current, basically. So it will, well, it is not the standard model, but I calculated, and so you better know. In 76, we knew all these things, and I proposed what can be done with the neutrino magnetic moment. Yes. So I didn't expect, but I showed this paper in my talk, not expecting your talk.
Sorry, yeah.
So any other question? So if not, let's start with the speaker again.
Thank you.
Okay, so Poonam is going to talk about the impact of NSI and augmented disabilities.
Okay, thank you very much. This is my first visit to Valencia and to Spain, and thanks, Mariam, for inviting me here. And so I'm going to talk about non-standard interactions at long baseline experiments. You can already see that neutrino oscillation physics has progressed enormously over the past many decades, and now nobody is really talking about what neutrino oscillations are. People are going beyond that and trying to even constrain or understand which direction of new physics one should take. And the most popular model or most popular scenario beyond the standard model is that of non-standard interactions, precisely because it is somewhat model independent. It just parameterizes our ignorance in some small parameters, and then we can translate it to a specific model when required. And so this is a little bit more general than specific models that one can consider. So my talk will be basically covering some ideas about how NSI non-standard interactions could impact measurements at long baseline experiments. In particular, due to shortage of time, I will mainly focus on the Dune experiment, but it's all applicable to all other long baseline experiments that are going on or will be happening in the future. The work done is mainly in collaboration with Masood, who is here, Animesh, Mary, who is at BNL, and these are the PhD students who are working with me. This is a joint student between Raj Gandhi and myself, and he's at HRI. So let me proceed. So this is the only slide I have on Dune because there is going to be a specialized talk on Dune by Carvera. So mainly it represents a baseline of 1300 kilometers. It's a long baseline. Neutrinos are going from Fermilab to the Sanford Underground Research Lab. This distance is like 1300 kilometers, and it is planned at an energy which is corresponding to the first oscillation maximum of the P mu E, and that corresponds to something around 2.5, but it's a wideband beam, and I will come to it towards the end of the talk, that why is this wideband nature helpful in, again, talking about new physics, etc. So the prime motivation for planning this experiment was to look for standard unknowns in the neutrino oscillation physics, which are precisely the knowledge about CP violation, octant of theta 2-3, or the neutrino mass ordering. We have some hints of those, but okay, still those questions are in the pipeline. So those are basically the primary science program of Dune, and there is also ancillary science program, which is including some new physics aspects, etc. But what I will be showing basically is that the new physics or the ancillary program has a very strong feedback on the primary science goals of an experiment like this. So let's proceed. I should introduce what non-standard interactions I'm talking about. They were precisely introduced in this seminal paper of Wolfenstein, this MSW effect originated from here. In this paper, he in fact mentioned that neutrinos could oscillate even if they were massless, provided the interactions were non-standard. Of course, we now know that the non-standard interactions or neutrino oscillations do not require non-standard interactions for explaining the flavor change, but a subdominant such contribution is still in the game. So what we will be interested in is looking for, let's assume, or because we cannot rule it out that there is no non-standard interactions, let's assume that there are some small subdominant effects due to this non-standard interactions, which can be parameterized in a model independent way and study what is their impact on the measurements. So the Lagrangian for the non-standard interactions is given by this, and it is parameterized by an epsilon. Here again it is V minus A or V plus A, as was introduced by the previous speaker. And generally in the oscillation context, propagation NSI or matter NSI are what are relevant. These are the neutral current interactions, and we are thinking of them as subleading effects in the discussion of oscillation, and they can severely impact determination of the standard parameters, etc., etc. We'll see. So this is how it enters the Hamiltonian. This is your standard part, and this is your non-standard. This is the standard matter effect part, and this is, so there are new parameters in the game, and this is a cartoon which shows what a non-standard interaction would be in comparison to a standard one. So what one gets is a flavor dependent refraction in the neutral current piece. So diagonal as well as non-diagonal terms are going to contribute to the flavor change. So let's come to one such important question, which is that of CP violation in neutrino oscillations. What does that mean? How does one infer signal of CP violation in neutrino oscillation? All these discrete symmetries, one can actually construct quantities which are related to probabilities. This is in the neutrino channel, this is in the anti-neutrino channel. If one has two flavors alpha beta, comparing this to, this is the CPA symmetry, this is the T, this is the CPT. And there is one very nice thing one can extract in the standard 3-flavor paradigm, if you assume CPT invariance, which is a good thing, and unitarity, one gets for 3 flavors that there is only one CP asymmetry quantity which is proportional to this famous Yarlskog factor. So the conclusion is that if there are 3 flavors only and if there is CPT invariance as well as unitarity, which one expects, then one would have this CP asymmetry in all the channels are equal to one another. And so if I want to make a conclusion, provided my physics is standard, if I want to make a conclusion, I can measure in any of these channels, and it would be the same thing. So one would actually get some information about this delta, which is the Dirac type CP phase, which enters the neutrino oscillation formalism. Now, if one looks at this expression little closely, one can actually write down the probability in terms of the vacuum parts, which are these 1, 2, and 3, plus matter and some subdominant terms. And CP violation signal, this delta, comes in the interface. So there are 3 mass scales in the neutrino oscillation context, 1, 2, and 3. And this is one splitting, this is another splitting, and the cross terms, which are the interference terms, carry the information about this CP violating phase. So in vacuum, this is what one has. And one can see that the CP asymmetry is directly proportional to sine delta times something under this approximation to leading order in this, as was shown in this work. So it goes like this. Plus, if there are matter effects, so this in vacuum goes as L over E. That's the point to remember. And in matter, what happens is that matter can, because matter is CP asymmetric by default, we have electrons, but we do not have positrons. So it introduces fake CP effects when neutrinos are propagating through matter. So what one can, those are referred to as intrinsic, which is what one sees in vacuum. That's that first part that I showed you. And in matter, you can get some complicated expressions like this, but the bottom line is the following, that if you plot the CP asymmetry as a function of energy, here the baseline has been fixed to this, what one sees is that as in vacuum, if delta is 0, you expect a 0 CP asymmetry, and that should be independent of the hierarchy. That's what one gets. Similarly, if delta is something non-zero, here it is pi by 2 or minus pi by 2, one gets something which is different, but it's again independent of the hierarchy.
So if delta equal to 3 pi over 2,
yes.
that is 0, net effect is 0?
Where? In matter?
Right.
No, actually there is a j sitting here. So that's a sine delta term. So it's a cos delta over sine delta times sine delta here. Yeah, that cancels. So it's not a problem. So in vacuum, one gets exactly the same copy here, but in matter, if it's normal or inverted, one gets something. First of all, the important consequence is that you get a non-zero CP asymmetry even for 0 value of delta. So one is having a confusion between what one is measuring as a CP violating parameter in presence of matter. One needs to disentangle these two effects, intrinsic and extrinsic. That's a very important problem. And then these effects for non-zero values of delta are basically mirror images here about this line. And so it's hierarchy dependent. So there is non-zero for 0 CP phase, non-zero asymmetry at large values of energy, as well as hierarchy dependence that one can see. Already we see that there is a fair amount of complication here. So now let's come to introducing the non-standard interactions in the game and see how the measurements of CP violation sensitivity, mass ordering sensitivity, etc. are going to be affected. There is a lot of body of work done in this direction, and I could not have done justice including few of them, so I have just restricted to our work for showing as a representative ideas. So here this is the CP asymmetry again as a function of energy. So here this is asymmetry plotted as a function of energy. The cyan bands basically represent what one can get in presence of standard interactions. When you plug in a small amount of NSI parameter, this is going from 0 to 0.1 only, you see that at large values of energy, if you also vary the phase, you can basically get very large asymmetry, -1 to +1. So this is the place where one should look for if you want to disentangle effects from standard matter effect to the non-standard effects. If you want to distinguish between the two effects, this seems like a good place. Here, where the flux is maximum at 2.5, around 2.5, the difference is there, but not so large. So this is, one also sees a saturation behavior at large values of energy. And one sure shot conclusion one can draw from here is that if you have large asymmetry, that surely implies some new physics, whatever it might be. So then one can check with the flux, realistic flux, plot the event rates. One sees that if you take the standard flux at Dune, what you get is flux that is, the event rates are falling off at higher energies. What it means is that if you use the standard flux, you are not going to be able to extract the information at higher energies. So there is a problem, although there was a large CP asymmetry at high values of energy, but if you were to extract that, it's a bit of a bottleneck because the flux is peaked at 2.5. And it has impact on the CP violation sensitivity that is shown here for some representative choice of parameters, which are these. These are as small as this, which is within the present constraints. You see that these gray bands are what tell us what the CP sensitivity would look like. So this plot actually shows sensitivity as a function of delta. If delta is 0 or pi plus minus pi, you expect no CP violation sensitivity, so it is 0, and it is maximum at plus and minus pi by 2. And here also same thing, but you see that if there is NSI present, even for delta equal to 0, you can get a large effect here. In addition to this, what one can also expect is that if you get the same value of sensitivity, it may imply some kind of degeneracies that are being there, that are present there, and one needs to basically then resolve those degeneracies in order to get a clear idea of what's happening there.
And these absolutes can bring their own phases as well.
They can also bring their own phases. So in this gray band, actually, there is a full phase variation in the allowed range. So that's what it is. And this dashed curve is basically for no phases. So if it's only the moduli, then it looks like this. So if we allow for the full freedom in the parameter space, then there is a big mess there. This is an example of mass ordering sensitivity. This is for what you have for the standard case, and these are for bands for the non-standard case. Again, plotted as a function of delta. These shapes, etc., come naturally for a given baseline, and that's all explained in the paper. So one sees again here that if delta was pi by 2, there is a degeneracy here. So one cannot be sure that it's coming due to standard interactions or non-standard interactions, or so on. But this also, one more point to mention here is that mass hierarchy sensitivity for 5 plus 5 years of neutrino and anti-neutrino runtime with Dune is going to be pretty nice. Much, much above 5 sigma. Okay, so let's come to the next question, another question that one can ask. I mentioned to you that there is this problem of intrinsic versus extrinsic CP violation, etc., and even non-unitarity effects due to that. Can one actually probe them in presence of new physics? So this we have studied in this work, where one has used this quantity which was actually introduced in this work by Jose and other authors, where they have considered this delta P CP, that's the same as the CP asymmetry. But if you consider a difference of the delta P's, one at pi by 2 and one at 0, the vacuum effect and the matter effect can be disentangled. And that works out to a very good limit in the context of separating the intrinsic and extrinsic components. Its only problem was that I think the phases could not be taken into account, but otherwise this quantity is a very good quantity. So what we did is we constructed these oscillograms for standard, non-standard, and sterile, so one can actually see the difference in different scenarios and understand those differences in terms of these. But what one can see is that all these long baseline experiments are planned at the first oscillation maximum, which is this curve, and more or less all of them have lighter regions. So the problem of actually inferring the intrinsic CP violation is a very hard problem. It's not going to be very easy. Even if one measures the signal of CP violation, to infer the intrinsic value of the CP phase is going to be quite tough. The other aspect that one can ask is that now there is a mess, there is a interference from new physics coming into the inferences of standard physics. So one would like to ask this question, can we separate the new physics scenarios, or any two scenarios A and scenario B, can we separate them using some idea? So here we've followed a very unconventional approach. We actually collaborated with an experimentalist, Mary Bishai, and we used experimental handles in order to attain what we are trying to ask. So here what we did was, we used high energy beam tunes that are possible for Dune. Dune is a wide band beam. So for a wide band beam, you have these different beam tune options. And we remember that I told you that the asymmetry is very large at higher values of energy. So naturally, a higher energy beam tune would aid in isolating scenarios from standard to non-standard. So we utilized that, and we showed that this is almost above 3 sigma for most of the values of delta, the distinguishability of the two scenarios. So this is this. And recently, we are also looking at now correlations and degeneracies of non-standard parameters with high energy beam tunes. And this is a work which is almost completed. It's in writing stage. Hopefully, it appears in this month. And there is a preliminary plot. So it is like parameter space plot between epsilons, different non-standard parameters and the phases, etc., and the delta and other non-standard parameters.
What is the size?
Sorry?
SI
Standard interaction. Standard interaction. So just for short, NSI and SI are on the same footing that way. So these are the parameter space plots. And here again, the high energy beam tune helps in constraining these parameters in some of the panels quite a bit. So that's something very interesting. And another work that we are looking at is now how we can have a geometrical visualization of effects due to these non-standard parameters. And that is a work that is also ongoing. And hopefully by January, we should be done with that. And that would be interesting because that will give us a new way of looking at the effects. Some part of the story might be missing in just doing the numerical analysis. So we'll have a way of quantifying those effects and understanding their significance. Okay, so I think I will just summarize. I think I can leave with this slide. And maybe if time is short, so I'll just leave with this slide and have some questions instead.
So Poonam, maybe you mentioned and I missed. So these configurations for the beam,
Yeah.
so this is the low energy, medium
Yes.
energy. So which is the one that is being considered?
Standard, this one.
The standard.
This is the beam, which is peaked at 2.5 GeV, which is also the first oscillation maximum of P mu E.
But do you think there are plans to change also, I mean,
This is experimentally feasible option. So there are whatever. These have been obtained by optimization algorithms, and these are feasible options one can consider.
but
So
maybe
these
the
are
collaboration can consider it in a later
in a
stage?
later stage, once the whatever bread and butter physics is done. At a later stage, one can look at this and do better from the point of view of new physics.
But not the high energy.
High energy is also possible.
Okay.
Yeah. So we just checked both options in combination with LE. And I think actually high energy gives better results than the LEME combination. So that's
But then the schedule for this
will be later, yes. But it's a different way of attaining this separability between the scenarios.
So any other question for Poonam? Everything was very clear. So thanks a lot.
Okay, thank you.
So next speaker will be Taran Takore from IFIC. And he will talk about invisible neutrino decay with atmospheric neutrinos.
Let's start by thanking the organizers for this invitation and this workshop. So here, as the title says, I will talk about concerning invisible neutrino decays with the two future atmospheric neutrino experiments. So here is the outline. So after a brief introduction to invisible neutrino decay, I will describe the analysis, the first analysis for the KM3Net ORCA oscillation experiment, which has been done in collaboration with Mariam's group here at IFIC. And the second example is concerning neutrino decay parameter with the INO experiment in India with this collaborator, Sandhya Shubhavati Goswami, and so on. So first, so the neutrino decays were originally proposed as the solution to the solar and atmospheric neutrino puzzles, but however, they were quickly ruled out as the leading order explanation in favor of oscillations. But in many models of beyond the standard model physics, they propose both visible and invisible neutrino decays. So in this talk, I will focus on concerning the invisible decays of the neutrino state nu3. So nu3 decays into sterile state nu4, which is not visible, and a iron. So these kind of invisible decays can be constrained either through cosmological analysis or through oscillation experiments. So from the cosmology analysis, we get a very stringent bound on the decay, which is this. However, I will not talk about this analysis anymore in this talk. So here, this is the Hamiltonian in the presence of neutrino decay. So here at 0 is the standard vacuum Hamiltonian, and this is the standard matter term. And to this, we add the decay term here, which is minus I times alpha 3. And alpha 3 is defined such as this. And in this analysis, we consider that this nu4 is a sterile neutrino state. It does not mix with the active flavors. Okay. So here I show two oscillograms. So here the top plots show the difference in the oscillation probability for the channel nu mu to nu mu between when you consider the decay scenario with the value of alpha 3, which is 10 to the power minus 5 eV squared. And this plot shows the difference in the oscillation probabilities between decay and the standard model for the appearance channel nu mu to nu e. So in both of these oscillograms, we find that the effect of decay is mostly concentrated at low energies, below 5 GeV. And as expected, these happen at almost vertical cosine zenith, which is almost horizontally going. I'm not sure why the legend and axis labels have disappeared here. But here, in any case, I wanted to show the effect of including the decay term. So this solid line here shows the nu mu to nu mu disappearance probability in the standard model. And if you start taking non-zero value of alpha 3, then the oscillation probability starts to reduce as expected. So this is alpha 3, which is 10 to the power minus 5. And if you increase alpha 3 all the way to 10 to the power minus 3, then the oscillation pattern is almost like dampened out, and experiments can clearly distinguish between the oscillation and the decay scenario. So for this reason, the value of alpha 3s, which are of current interest, are in the range of 10 to the power minus 5. Okay. So next, I will talk about the KM3Net experiments. So tomorrow morning, a dedicated talk on KM3Net is scheduled by Huan De. He will give a full overview of this experiment, but here I will quickly flash through the important experimental details which are used in this analysis. So KM3Net is being constructed in two different configurations. They are called as ORCA and ARCA. So ORCA is optimized. It's designed to perform oscillation measurements with atmospheric neutrinos, whereas the ARCA configuration is being optimized to observe very high energy neutrinos from astrophysical sources or to perform indirect dark matter searches. So here is a very simple layout of the ORCA configuration. So basically, it's very similar to the ice cube, where you deploy about 150 strings of digital optical modules like this. And here is a picture of one of these dome units. So ORCA is operating on the water Cherenkov detection principle. It means that we observe the Cherenkov light produced in the from the outgoing particles produced in a neutrino interaction. And here this is an important number to keep in mind. So the instrumented mass of water is about 8 megaton, which is huge compared to the other experiments like Super K. Okay. So here, this slide shows the two basic event topologies which are observed in the ORCA detector. So we have track-like events and shower-like events. So a charge current mu event will produce a muon in the final state, which gives rise to a long track such as this. And mostly any other type of events, like CC nu E event or hadron shower will produce shower-like events such as this. So in ORCA, we do not have event-by-event separation between neutrino and anti-neutrino. So here, this plot here shows the efficiency of event classification. That is, like, given an event, how do you classify this as a track-like event or a shower-like event? This is plotted as a function of energy. So this kind of analysis is performed using some sophisticated machine learning techniques. And for the primary goal of ORCA, which is to measure the neutrino mass hierarchy, this classification is one of the very important parameter consideration. So as expected, most of the charge current mu events are classified as track-like events, and the other type of events are classified as shower-like events. And here, the effective mass of the detector is plotted as a function of energy for different neutrino flavors. So with this effective masses, when you calculate the event rates, we find that for 1 year of full ORCA operation, we obtain these kind of events, which is in 1 year a total of 50,000 events, which is huge. It's really a huge statistics. So this huge statistic is what drives most of the oscillation parameter measurements. Here on this slide, this plot shows the neutrino energy resolution plotted as a function of energy. And the bottom two plots shows the resolution of measuring the zenith angle, cosine zenith, for the track-like and shower-like events. So energy resolution is about 25% at 10 GeV energy. And the direction zenith angle resolution is about 5 degrees at 10 GeV. And this improves to 5 degrees, especially for shower-like events. Okay. So using the inputs which I flashed in the last 2-3 slides, we use this formula to calculate the event rates. So here, like for a given interaction channel, whether that is like charge current or neutral current, and for a given neutrino flavor, you calculate the event rate. And this is further folded with the event classification efficiency, or as we call it, as the PID efficiency of outcome. Now, for this sensitivity studies, we generate a fake data set using the current best fit values of oscillation parameters, which are described, this analysis is described in this paper. So noticeably, I point out that we are using sin squared theta 2-3 in the lower octant, and we assume normal mass ordering. So this is the main result for our analysis. So this plot shows the sensitivity to parameter alpha 3 for 3 years, and this is for 3 years, 10 years. This is the statistical chi-squared and very marginalized over systematics, and the oscillation atmospheric parameters theta 2-3 delta m square atmospheric, it lowers here. So this is the main result of the analysis. So for 3 years of runtime, tau 3 over m3 can be constrained to this number, 1.4 times 10 to the power minus 3. And this scales very nicely if you, for 10 years of runtime, because this atmospheric oscillation analysis is dominated by statistical errors. So then here on this slide, I show the impact of considering a neutrino decay model in the fit on the measurement of the atmospheric parameters, sin squared theta 2-3 delta m squared atmospheric. So to generate this plot, we set alpha 3 to 0, that's the standard model case, in the fake data set. And alpha 3 is kept as a free parameter in the fit. So here, the solid region shows the precision obtained in the standard model case, and the black contour shows the precision if you let alpha 3 be free in the fit. So we see that there is a negligible impact on this measurement. So, however, like as I will show in the, this is the case which happens when alpha 3 is taken to be 0 in the fake data. But if you take this to non-zero, then as I will show in the case of INO, the precision on sin squared theta 2-3 it is affected. Then similarly, we try to see the impact on neutrino mass ordering sensitivity. If you let alpha 3, if you keep alpha 3, if you vary alpha 3 free in your fit. So we find that the mass hierarchy sensitivity is not affected for the region of interest, which is this, alpha 3 around 10 to the power minus 6 here. Yeah. So moving on to the second atmospheric experiment, which is the ENO experiment in India. So this experiment is proposed to be located in southern India, and this experiment is basically a giant electromagnet. That's why the name 50 kiloton magnetized iron calorimeter. So this the detector is planned to be set up in a 3 kilometer steep tunnel under a mountain, which acts as the cosmic neon shield. And the active detection element for the iono-Eichel detector is the resistive plate chamber. Schematic diagram is shown here. And this detector is magnetized with a field of 1.3 Tesla, which enables separation between neutrino and antineutrino events. So this whole setup is optimized to detect charge current interactions of nu mu in the energy range 1 to 10 GeV. this slide, we can see the important parameterization of the INO detector. So here, energy resolution is plotted as a function of energy. Here you can see the resolution of cosine zenith. So at 5 GeV, the energy resolution is about 10%, and because the zenith angle resolution is approximately 1 degree at 5 GeV. And the bottom two plots shows the efficiency of event reconstruction and charge identification, which is very high, above 1 GeV. So here, this table shows the oscillation parameters used to generate the fake data set. So there, unlike the case of KM3net Orca, theta 23 is considered to be maximal here. And these two plots shows the event distribution for two different energy ranges. So as expected, starting from the standard model case, when you turn on the neutrino decay dump, the event rates go down. So this is the main result for the INO sensitivity analysis. So here, for 10 years of runtime, it can constrain tau 3 by M3 to this number, which is comparable to Orca sensitivity for 3 years. And here, lastly, on this plot, we see the impact of freeing the value of alpha 3 in the fit, as was done in the case of Orca. But here, this plot is generated. In this plot, we generate the fake data set with a non-zero value of alpha 3, which is 10 to the power minus 5. So because of degeneracies between alpha 3 and sine squared theta 23, we see that here, when you consider neutrino decay in your fit, sensitivity to sine squared theta 23, it worsens by approximately 4%. Okay. And here, finally, on this table, we see the comparison of these upcoming atmospheric experiments, Orca and INO, with the previous measurements, which are shown in these 3 rows, K2K minus and super K1 plus 2. So here, we see that the sensitivities are comparable to the limit shown in this analysis. But on the other hand, if you consider the sensitivity coming from the long baseline experiments, Minos, T2K, and NOVA, then both Orca and INO are improving the upper bound by at least an order of magnitude. And then, again, if we compare the upcoming reactor neutrino experiment, Juno and Dune, so we see that these 2 experiments constrain the parameter tau 3 to M3 to the order of 10 to the power minus 11, but still the atmospheric experiments are doing better than those. So that's because here you get a much longer baseline. So yeah, that is all from me. So to conclude, the atmospheric experiments, KM3net Orca and INO IKL, they look very promising to improve constraint on invisible neutrino decays. And this limits coming from the oscillation experiments, they will be complementary to the cosmological bounds. Okay.
So I don't know, Tarakit, maybe you can comment about the status of the INO proposal. If you have any news or...
I'm not the most updated on this, but I think recently it came out in the news that about 1 or 2 months ago, one of the necessary permission was issued, but they are that is subject to subject to the grant of 2 more permissions.
Okay, so still is not clear the situation.
Yeah, no.
So then, even if it is, what will be the schedule? Because now they need, the laboratory has to be excavated before, and then. So
yeah. So like in my opinion, like if the construction of the experiment is delayed anymore, then it will not be, INO will not be the first experiment to measure the neutrino mass hierarchy as was the goal.
The main purpose. Okay. Yeah, that's a pity. So, no more questions. So let's go for coffee, but let's find Taras before.